last week there was nothing to it. It was just finite matrices and various formulas how to manipulate their eigenvalues. They're all identities. There is no issue of convergence. There is no, deep issues of ergodicity. There is nothing. But that's the backbone of everything. So if that didn't work out, I'm killed. Now, what was wrong with last week, it was a good mathematics, very simple mathematics, but it was very bad physics. In the sense that what we did last time, we learned how to count. And, this counting is fairly simple. From here, you can get to there. And if you give yourself 7 time units to do it, there are roughly 2 to the 7th ways of doing it. And they're very precise formulas that keep track of it. But that's not very helpful in physics because you would like to know how important things are. It could be that going from here this way is very important, but going from here that way doesn't really matter very much, or almost happens never. But we gave everybody value either 1 or 0. And physically that can be right, because we know that certain ways of getting from here to there are very difficult. Other ones are maybe very likely. And for that reason, ergodic theory, which is a very sophisticated subject, and I find it harder than quantum mechanics, at least as mathematics is concerned. Somehow foundationally we feel more comfortable with it, but it's very hard. Ergodic theory, when they define dynamical systems, they don't say it's state space and law, but then they put some other letter here. And they tell you how they measure things. It's not just, where you are, how it happens, but how do you look at it? And everything depends on this. And this is this thing that you tend to not appreciate as when you learn physics, which is, when you get to quantum mechanics, they tell you it's all on Hilbert space, and you learn the word Hilbert space, and you're happy, no problem. But there are all these other function spaces, which we try to avoid as much as we can, but we really cannot. And in ergodic theory, there is a great difference between functions that are smooth and functions that are no place differentiable, maybe discontinuous, etc. So, C0 functions or whatever. Now, in applications, smoothness is the right thing. So we are rescued by the bell. But the mathematics that does this is not very smooth, because we're using deterministic equations, and they are infinitely precise, and there is no assumption of smoothness built into them. So the main conceptual advance in this field happened in late, probably not fair because there's a long chain between Poincaré, Birkhoff, and today, but combining dynamics and measure theory, or what we call chaos and what mathematicians call ergodic theory, happened in the 70s, where people introduced the notion of natural measure. So this was probably comes originally from Kolmogorov and other Russian people, but it was formulated in a way that we use it by Sinai, Bowen, and Ruel. And it's deep, but the basic idea is simple. We can define lots of ways to measure, but they should be robust in some sense, because in our world we cannot afford to measure things with infinite precision. So whatever we do should be in some sense robust to small errors and small imperfections. And this is the basic idea behind natural measure, but I'll try to define it now step by step.